Mark Miller, and I'll be speaking today about higher order smart contracts across chains. The world economy, the phenomenon of markets that has evolved in human society for thousands of years, is a very rich, complex phenomena that has given rise to all sorts of ways that humans cooperate with each other in large networks. And the current way that we're building smart contracts is not able to reproduce that richness. And in particular, I want to focus on one particular source of that richness that we can understand and try to do a better job to reproduce, which is the abstractness of property rights. Property rights evolved from very simple concept that there's physical goods and there's territory, which became tradable land, and you traded this thing for that thing. And it probably started without even a general concept that all these different things were under a common concept of property. But as people traded one thing for another, there came to arise this general understanding that, oh, these are tradable things. There's this concept of property. And then as people built institutions, as institutions grew, institutional arrangements, ways of transacting with each other grew around the concept of property, that was created this richness, this vocabulary of ways of cooperating with each other that were parameterized by whatever would feed into those arrangements under the label property. So once we had that, we had the ability to generalize the label, to label new things as property that had not previously been labeled property. And as we labeled new things property, the existing vocabulary of arrangements of cooperation, we were able to leverage them, to reuse them, to apply to any new thing that we came to call property. So in computer science, this process of building up a variety of abstractions that are generically parameterizable over some category of input is known as parametric polymorphism. And the ability to take new concepts and fit it into an old category so that parametric things that were generally parameterizable could apply to them, is known as reification. So Hernando de Soto, in the book The Mystery of Capital, examines why it is that the informal economy, the economy that exists outside of formal legal systems, he examines the nature of that economy. First of all, explains that it's a very rich economy. It's a genuine economy. A tremendous fraction of the world's overall economic activity occurs outside of any legal system, occurs in the informal economy. There's certainly much creation of wealth, much cooperation there, but they're not able to engage in the rapid growth of the rapid exponential growth of wealth creation that is familiar in our world. And Hernando de Soto asks why not. And he focuses on what he calls turning a property into capital. That it's a failure to turn property into capital. So in our world, we're familiar with complex networks of abstractions of property arranging composition of cooperative arrangement. So we have the concept of, let's say, owning a house, but then we have the concept of mortgaging a house. Well, mortgaging a house creates this new valuable arrangement, but then once you've mortgaged the house, you don't own the house. How is it that you can sell the house if you don't own the house? Well, what you do is you sell your position in the mortgage contract. That the position in the mortgage contract itself becomes a new abstract form of property. You can think of it as a derived right, where the house itself is the base right. And the example that Hernando de Soto gives in Mystery of Capital is the inability to turn ownership of a house, what is genuinely, from an economics perspective, ownership of the house, but ownership that is not legally recognized by the external world legal systems. It's recognized by the systems of norms in the local community, that a particular person is recognized as owning the house. Within the local community, they can sell the house and the new owner is recognized as owning the house, but they can't take that internal recognition. It doesn't fit the vocabulary of rights that these other external built-up arrangements of cooperation understand. So there's just this inability to reify. You can think of this as a reification failure. And the reification failure means that this whole built-up richness of institutions that we have in the rest of the world cannot be parameterized by the property rights created in the informal economy. So I want to recast de Soto's insight very much in computer science terms so that we can use both the economic perspective and the computer science perspective on this one phenomenon to build smart contracting systems that can enable a greater richness and complexity and composability of cooperative arrangements. So in computer science, we have this notion of higher order composition. And for each form of higher order composition, it depends on some ability to reify, and those abilities, each time you have an ability to reify, there's some case at which it runs out of steam, and you no longer have an ability to reify within that system. And now that failure to reify should provoke you to build a new higher order system that has new rules of reification so that you can now bring this higher order composition into that new realm. So this is all very, very abstract. I'm going to start off a little bit less abstract. So in the world of functional programming languages, where you have pure functions, the really cool thing about functional programming languages is functions operate on values of some sort and will compute a new value given input values. But a function itself is the kind of value that you can apply functions to, and you can write many functions, like a function composing function, which are generic, that will take any function as input. So the kind of thing they are as a means to manipulate values, the kind of thing that they manipulate, which is the values that you can feed into the function, is also the kind of thing that they are. So therefore, they are the kind of thing that they manipulate. And therefore, you can compose them into these great networks of functions operating on each other and eventually on base values, and create the richness that we associate with functional programming. However, functional programming is specifically mathematical-like functions with no side effects. The world has stateful concepts like a bank balance. And you can't take a mutable bank balance and reify it as an object, as a thing that is the kind of thing that plays within the world of higher order composition of the functions. You can write patterns of functions. You can engage in these other patterns with monads and state passing and all that, that end up creating a new level of abstraction. But you can't simply apply a function to a stateful object and have it be the same stateful object after it changes state. So instead, we have object-oriented programming, which has this higher order nature with regard to stateful things. That you can take a mutable object, store it in a table. While it's in the table, it might change state, and then later you can pull it out of the table, and it's the same object in the new state. That's an example of a kind of composition, a kind of higher order composition to create cooperative arrangements of computation that you simply can't do in a direct manner in functional programming. And when you build up patterns that do that, you're creating, for example, a new object layer of abstraction that's really distinct from the functions. However, what is directly relevant to our mission of trying to bring the world economy online through digital media, through blockchains, through smart contracts, is that objects themselves cannot directly represent exclusive rights. You can create patterns of objects, as you will see, by which you indirectly create the concept of exclusive rights and indirectly manipulate the exclusive rights. But the exclusive right itself is not an object, is not reified as an object. So in the same way that you can create patterns of functions that give rise to this new level of abstraction of objects, we can create patterns of objects that give rise to a new level of abstraction of electronic rights. And that's what we're doing. But we're not just trying to reify electronic rights, we're trying to do it in a higher order manner so that contracts manipulate rights, but a contract that unfolds over time, like a mortgage, any contract that unfolds over time, the continued participation in the contract is a derivative value. It is a valuable role. It's a valuable position to be in, and we want that valuable role to be a valuable tradable right, and to conceive of the concept of rights as a generic vessel, so that a very great variety of kinds of rights can be fit into that vessel, where the vessel has to be broad enough to fit many things into it, but it has to be strong enough such that you can write a very wide range of market institutions, of kinds of contracts, exchange, options, various forms of derivatives, auctions, et cetera, et cetera. We found that we could write these things in a generically parameterizable way, in a way that was parametrically polymorphic over rights, in a way that is very much analogous to what we've seen before. So what we're trying to achieve is, by enabling this higher order composition of rights and contracts, this is much of the richness of the real world, of the thousands of years of evolution of market institutions. It's that those deep networks of contracts interacting with other contracts, of agreements and arrangements interacting with other agreements and arrangements, that is the source of the richness of the world of the market. Without this higher order composition, we're not going to reproduce that richness. Where we have had higher order composition, functions and objects, we have seen in the computer world a richness of composition. Where we have not seen higher order composition in the existing world of blockchain and smart contracts, we have not seen deep networks of cooperation. However, with proper humbleness, we should understand that we're probably taking a step that is also at some point going to run into a reification failure. It's early days yet, so we don't yet have a painful reification failure to talk about, but we should expect that eventually the process repeats again, there is a reification failure, and there will be a need to create a pattern at this level that can create yet another level of abstraction. To provide orientation about what we're doing, I'm just going to show the architecture Agoric is building, but we're, in this talk, only concentrating on the upper layers of it. So just very briefly, each rectangle here, each purple rectangle is an individual machine. Each stack is a logical machine. The stack on the left is a public blockchain. It's a logical machine that's built out of massive multi-way agreement between many physical machines that all cross-check each other. And that logical machine becomes a credible platform for running programs that need wide credibility, that need everyone to believe that what the program seems to have done is what the program legitimately did. And then there's individual machines and non-blockchain replication, and some of these things will be proprietary inside companies, and some of them will be in the public. What we want to do is we want to build a level of abstraction over that so that you can interact across the network in very much the way we are used to with distributed systems across all of these different platforms. And on top of that, we're building our object capability layer. So our object capability layer is a secure form of object-oriented programming where the object reference, the pointer to an object, is a write, and message passing is a form of rights transfer. And we're building this to, again, span over all of those platforms. And I'll just briefly mention why that form of spanning is so powerful. One of the things that we're used to with the web is that the web is mostly a public system. However, companies have internal websites behind the firewall that contains information that simply nobody intends to make public. But the users within the firewall can follow links from internal web pages to external web pages in a completely seamless manner. So we believe the same thing is true for the upcoming world of cooperative distributed secure computation, that we want to span private and public, where the public use benefits from a large volume of private use interconnecting to it, and likewise the private use benefits. Markets are all about network effect, and if we can span both of those worlds so that the logic of it seamlessly interpenetrates, we can add value to both. However, this is a world of objects. It has exactly the reification failure I was just mentioning. We're not able to reify a tradable right directly as an object. So we build patterns of objects that create this new level of abstraction, which we call the erights and smart contracts. And there's this duality here. It's exactly the duality that I mentioned, for example, with selling a mortgage. It's that contracts manipulate rights, and a contract that unfolds over time creates tradable rights, and many contracts can be generically parameterizable so they can form these cooperative networks. And our system comes in a protocol stack where each protocol builds each level of abstraction out of the previous level of abstraction. We have something called VATTP, which we're reconciling with the IBC system from Cosmos that builds the VAT level of abstraction out of the machine level of abstraction, CAPTP that builds the object level of abstraction out of the VAT level of abstraction. Neither of those are relevant to the talk. What is relevant to the talk is ERTP, which is the Electronic Rights Transfer Protocol. And that is the means by which, starting with distributed secure objects, we can build a system of tradable rights and smart contracts that facilitates higher order composition. So an object reference in a memory-safe object programming language is already a form of right, even before you go from there to object capabilities. If object Bob does not have a reference to object Carol, then in any memory-safe object programming language, object Bob simply cannot invoke Carol. He cannot make use of Carol's public API. He cannot provoke whatever behavior would be provoked by invoking Carol. However, if Alice, who has a reference to both Bob and Carol, invokes Bob passing Carol as an argument, that is both Alice exercising her right to invoke Bob, granted by her reference to Bob, as well as Alice authorizing Bob to invoke Carol by providing the reference. And now that Bob receives the reference, he can invoke Carol. So to get from objects to object capabilities, we impose the constraint that these references between objects are the only carriers of causality. There's no other form of causality outside the system. This makes the reference graph from the programming language literature identical to the access graph from the access control literature, so that the richness that object programming already gives us at manipulating the reference graph, we leverage that intuitively as a direct extension of object intuitions for manipulating the access graph, for manipulating security relationships. And the result is that we can express what would normally be thought of as complex security relationships very straightforwardly with simple object code that's easy to explain. So on the left, we have our object layer. On the right, we have Alice paying Bob in some amount of money as an example of the kind of E-right that we want to support. Let's use the contrast between objects and money to explore the differences between these layers of abstraction. So objects are shared. Once Alice gives Bob access to Carol, there's still this line on the left, the diagonal line, by which Alice still has access to Carol. And Alice might drop the reference, Alice might drop the reference, but Bob has no way to know that Alice has dropped it. Whereas for Bob to get paid, to consider himself to have been paid, he needs to know that he has exclusive access to the money that Alice gave him. Objects are exercised. They perform actions. The whole point of having a reference to an object is you can do things by invoking it. Whereas money is symbolic. It doesn't have any use value. It only has value in trading. Objects are opaque. When Bob receives this reference to Carol, all Bob knows is he's received a reference to some object that somebody who could invoke him decided to give him. Whereas Bob, in order to consider himself to be paid, needs not just to have received the money, he needs to know that he's received the money. And he needs to know that he's received what money. To know that he's received 3 units isn't any good if he doesn't know if those are gold coins or dollar bills or euros or whatever. So he has to be receiving something where he understands the quantity it is that he's received. Objects are specific. Bob receives exactly Carol itself, that particular object. Money is fungible. Bob doesn't care what dollar bills he's received. He just cares about the total quantity he's left with at the end of the day. So I'm drawing this contrast not to say that objects are the left column and E-rights are the right column. Objects are indeed the left column, that's accurate. But by E-rights, I include all of these variations, all these degrees of variability that this contrast has shown us 4 of the dimensions by which rights can be different from each other. And by erights, we want to include all of the variations and combinations that the contrast between the two has shown us as a world to explore and build. So fortunately, the patterns you need to express in objects to build erights are straightforward. This is the code needed to build the money with the attributes I just showed out of objects with the attributes I just showed. So over here, we have an outer function called makeMint, and each time we invoke makeMint, it makes an issuer object over here, a ledger object, and a mint object, and it creates this layer in which those 3 objects are in bed with each other. They know each other. So let's go ahead and, so this layer, this plane, represents a logical new currency. So let's invoke makeMint 4 times, creating 4 different systems of currency, all of which instantiate the code on the right. The mint object is where new units of currency come from. It makes a purse initialized with those units. So let's go ahead and create some new units and give Alice a purse containing, let's invoke a purse containing $100, and let's invoke mint again, creating a purse with $200 that we give to Bob. So we consider this to be Alice has a right to 200 units of, let's call it gold coins instead of dollars, that Alice has a right to 100 of them and Bob has a right to 200. But notice that the rights themselves do not appear in the diagram, and the rights themselves do not appear in the code. They are not objects that you can store and retrieve from other generic objects. Now let's say that in this arrangement, Alice wants to buy a concert ticket from Bob. So what Alice does first is she sends the withdraw method to the purse. And what the withdraw method does is it makes a new purse. So the Alice's main purse creates a new payment purse, and then consults the ledger and moves 10 units from the main purse to the payment purse. Then Alice sends the payment to Bob, and with this buy method, this buy message, where the buy message says, contains the payment and also a description of what Alice wants to buy. And now we have an interesting dilemma. You might think that Alice has reified the payment in the payment purse. We even called the object payment. So as far as Alice is concerned, at this point she's paid Bob. But we colored that reference error red because Bob has no way of knowing that Alice has dropped it. Alice might still have access to the payment purse, but that's not our only problem. There's also, Alice knows that she sent a purse whose purpose was to pay Bob, but Bob doesn't know this yet. He's just received some object from Alice. He doesn't know what it is. But objects are exercisable. You can invoke them. So we can use the behavior of the objects when invoked to bring about the change of state that represents, at our higher level of abstraction, the motion of rights. So going back to our code, Bob does this by sending a deposit message to his main purse saying, deposit into yourself 10 units from the argument purse. These purses consult the ledger, change the ledger's representation of that. And at no time has Bob revoked Alice's access to the payment. Bob cannot revoke Alice's access to the payment object, but it doesn't matter because now the payment object is associated with 0 units. Bob has revoked the usefulness of the payments object. But Alice still has access to it, but it does her no good. The code that I showed you created erights out of objects, but it did not yet fit into our framework for creating higher order composition of contracts in a smooth way. So I want to be realistic about how much code it takes to do this for real, and that's the code on the right, which I will not go through. But I do want to emphasize something about the previous piece of code, this code, and every piece of code you're about to see in this talk, which is, well, these things are operating on blockchains and not blockchains and creating cryptographic interactions that represent distributed money protocols and other forms of cooperation. Surely, if they're doing this cryptographically, the code must be expressing cryptographic concepts. And the answer is no, that it isn't. The answer is that that's one of the things that we're buying with our layer separation, is designing new cryptographic protocols, designing new arrangements of cryptographic primitives is bloody hard. And experts get it wrong all the time. And if every time we need a new complex cooperative arrangement, we have to do it by figuring out a new arrangement of cryptographic primitives, our new economy is sunk. We're not going to get there that way. Instead, our approach is to invest that effort once in the cryptographic this is actually a first approximation. It's not quite true, but it's sufficiently true that it's the main truth of programming in the system, which is we invest the effort in building the cryptographic protocols once, the very hard effort, to create the system of distributed secure objects such that once we've got the power of distributed secure object capabilities, we can now take a great variety of cooperative arrangements and express them simply in terms of objects and object behaviors without ever needing to refer back to cryptographic concepts. So, having built patterns that express erights, we're now going to think about things at this new level of abstraction that we've created, where the eright itself is now thought of as an object that moves. So we'll use that as one visual language where you still have issuers and purses, but the erights move between them. We'll also use the visual language where the eright is just carried in a message. And in this case, Alice buying a ticket from Bob through the code on the right. Once Alice receives the payment, when Bob receives the payment, Bob is able to know that he's been paid before releasing the concert ticket. However, this protects Alice from Bob. This protects Bob from Alice. It does not yet protect Alice from Bob. As far as this arrangement is concerned, Bob could simply pocket the money and never release the ticket. So this is still not an adequate set of primitives to start down on the road to rich composition of markets. We need to go from this picture to a picture that includes smart contracts, including a smart contract that brings about an exchange as an all or nothing exchange between two parties, that either that Alice knows she won't lose her money unless she gets the ticket, Bob knows he won't lose the ticket unless he gets the money. So over here, this is just a rearrangement of the elements you've already seen. We have the money issuer in the upper left. We have the ticket issuer in the upper right. Alice has a main money purse and a main ticket purse, and Bob likewise has a main money purse and a main ticket purse. We introduce a new concept called a contract host. And this is, more than anything, the kind of code that you would run on a public blockchain, because this is the piece of code that needs the massive multi-way mutual credibility that you get by running code on a public blockchain. So this is the thing that Alice and Bob and a million other contracting parties would have common knowledge of a particular contract host. And what the contract host does is it accepts code from Alice and Bob and whoever else knows the contract host. And the highlighted line here is where the contract host starts a contract. So let's say that Bob submits a escrow exchange contract. So now the escrow exchange contract has been set in motion by the contract host. And what the escrow exchange contract does is it creates two roles for participation in the escrow exchange. And then the contract host takes that and turns them into seats that Alice and Bob can sit in, which is their ability to continue to participate in the contract. And now that Alice and Bob can participate through these seats, they can send, Alice can send in the money that she would like to use to buy the ticket. Bob can send in the ticket that he would like to offer to get the money in exchange. And the escrow exchange agent will just go to the issuers and obtain both of those rights and verify that it has obtained the rights, that it has obtained from Alice the rights that Bob demands, and that it has obtained from Bob the rights that Alice demands. And once it has verified that, it can release the coin into Bob's main coin purse. It can release the ticket into Alice's main ticket purse. So an escrow exchange is fairly immediate. A much more interesting example is the covered call option, which is, let's say that the reason that Bob wants to sell the ticket is he's bought a $500 ticket to a concert that he wants to go to, but now he finds that, oops, he has a conflict, he's going to be out of town. He wants to sell it to Alice, but Alice doesn't know if she really wants to attend. She needs to make some other plans, so she'd like to reserve the ticket. So she says, okay, Bob, if I give you $10, can you just hold on to the ticket, reserve it for me for a few days so I can make some other dependent plans? So, so Bob's reservation, if Bob agrees to reserve it, that's a covered call option. It's very much like the covered call options, the things called covered call options, which are derivative instruments in the financial industry, just logically the same relationship. And the covered call option, it's more interesting than in the escrow exchange. It's more complicated. Why is it so much less code? It's because this piece of code actually wraps the escrow exchange code. It uses the escrow exchange and front ends it in order to create the differences between a covered call and an escrow exchange. So how does a covered call differ from an escrow exchange? Well, first of all, the ticket is pre-escrowed until the covered call option has the ticket safely squirreled away where only it can transfer it. There is no covered call arrangement for Alice to participate in. It doesn't exist until the ticket is in escrow. Also, with the escrow exchange, either party can at will cancel the arrangement. With the contract host, Bob has given up the right to cancel. The cancellation is instead held by a timer created by the contract host. And other than that, it's the same, and it uses the escrow exchange underneath the surface. It delegates all the hard work to the escrow exchange. The result is that now Alice is in this valuable arrangement. But now that Alice has this reservation, let's say Alice finds that, oops, she does need to travel anyway, or she can't make use of it. She knows Fred happens to be interested. Maybe she'd like to sell the position in the reservation to Fred. So this is higher order composition. This is every time we create a contract that unfolds over time, we have created a derivative value. We've created a situation that is a valuable situation to be in. And to bring about higher order composition of rights and contracts, we need those derivative values to themselves be derivative rights. So we bring that about by having these seats that are created by the contract hosts in reaction to the contracts that they're running, asking the contract host to create a seat, that these seats are actually represented in a seat issuer, that the covered call option, there's an issuer for the right to sit in that seat that the contract host has created. And now for the covered call option, this is basically functioning as the seat where Alice has the ability to participate. But for the escrow exchange option down here, it's acting as an issuer. So to this contract, the issuers are gold coins and tickets. To this contract, the issuers are the seat issuer and the silver coin issuer over there, where Bob would buy the covered call option for Alice for these silver coins. So these seats as derived rights, as derived tradable rights, show us, demonstrate that this taxonomy we've opened up is a genuine taxonomy. It really does open up a rich space of kinds of rights. This seat, this ability to continue play in the first contract, like money, is an exclusive right. The purpose of obtaining the seat is the possibility of exercising it, of making use of it, of bringing about the behavior of the upper contract. That's the right being traded in the lower contract, is the ability to bring about behavior in the upper contract. So therefore, that right is exercisable the way an object is exercisable. In order for Fred to buy it, it needs to be assayable. And this is actually where the interesting problems are, the interesting design issues, is the upper right, the derivative right, is created by an arbitrary program that is the smart contract that has to be designed to fit into the framework, but it's some arbitrary program that has been designed to fit in the framework. Nevertheless, Fred has to be able to describe what role it is that he's trying to acquire, what the nature is of what he's trying to be able to continue play in. So these seats are assayable in the way that money is assayable. And then the thing Fred receives is the right to continue play in a particular contract, this particular contract that Alice and Bob started. So therefore, it is specific the way objects are specific. And now I will take questions. This is more an observation, but it's worth, if you go back to that previous slide. There. One of the things that I have observed about like ERC20 tokens or ERC721 is that they are, reproducing some of what it means to have objects or object pointers in a sort of clunky open-coded way. But the fundamental thing that in this spectrum that is different about them is they are only symbolic. Mm-hmm. With an ERC20 token or ERC721, it can't have exercise.
Mm-hmm.
That's something that gets in the way. So I can't have a concert ticket that I can ask the venue of.
Mm-hmm.
I just have a token.
Right, and the other thing is that the fungible tokens and the non-fungible tokens are like completely different from each other, and nobody writes over here, if I write an auction, some like a second price sealed bid auction or English auction or Dutch auction or a continuous double auction, all of these things, as well as these derivatives, this very wide range of things can be generically parameterizable, where you can feed them, where they can bring about transfer of things that are fungible or not fungible, et cetera. And the other, that's also addresses this issue of being able to build and use and compose cooperative arrangements with confidence, so that people of more normal skill, people whose expertise is elsewhere in their subject matter that they want to cooperate about, rather than having to be deep experts in smart contracting, is the highly reusable nature of the components means that you can have the same kind of wide spectrum of effort and expertise that we're used to from normal software engineering, where some components are designed very carefully, but they're highly reusable, so that they can now be, so that now that they're heavily vetted and well understood, they can be applied with confidence, and then these simple wrappers, the simple compositions, can then be simple and simple to understand. And one of the key things about object capabilities, as opposed to other security architectures, is to support compositional reasoning about correctness, even in regards to matters when there are multiple interests and rights at stake. This is something where the main security paradigms, identity-based access control, which Ethereum and the conventional smart contracting world we see today is mostly trafficking in, we know that it does not support compositional reasoning about correctness with regard to such security matters. So high reuse plus compositional reasoning about correctness enables simple compositions of complex but highly reusable components to be done with confidence. Come on, more questions.
Yes, I was struck by the discovery aspect here. What's really exciting about this is that you've got discovery in rights that are going on, continuously unfolding. And we've never had that before. It's almost the opposite of that, that you have a set of rights and then the discovery process is largely about how to exploit that or exploit the counterpart in this. Whereas this actually does create high-powered incentives to discover rights that can be built on.
Yes.
And are valued to others, yeah. Yeah, that's not a question.
Well, it's a wonderful observation. I certainly appreciate it. Kate, yes.
So in a world that has thousands, if not millions, of different kinds of rights, how do you expect people to be able to talk about them? Or how do you even expect them to be able to direct their computer agents to to be able to choose the right kinds of rights to buy and so forth?
So I'm going to take the strategy of reducing this to a previously unsolved problem.
Can you repeat the question?
In a world where there are millions of different designed kinds of rights, lots and lots of different contracts creating lots and lots of derivative rights, how do you expect people or the programs people write to be able to navigate that and understand what right they want to trade in and what that right means? Kate, am I getting that? Okay, good. Reducing it to a previously unsolved problem, conventional software engineering is able to build up tremendous, rich world of software that has really created the modern world without solving that problem either with regard to objects. But what we found is that we can go a great distance without solving the problem. There's lots and lots of different interface types and lots of different APIs that essentially solve the same problem in ways that are not interoperable. And we've got GitHub and just all sorts of communities and ways to interact with each other to become informed about what to use for what purpose, what things seem to be better at it, which are pleasant APIs to use it through. Then we have things like package managers, et cetera, that have various forms of description, including prose and listing of dependencies. So that all of the great variety of categorization and explanation and search and discovery that we have with regard to the great diversity of object APIs, I think that that's a strength. It means that the world is tolerant of having a great diversity, that the richness of a great diversity gives us a richness of experimentation, a diversity of ways to provide functionality, and it does it at some cost at making discovery harder. And then we build up these other institutions to try to ease the discovery process without reducing the variation. Bill.
I'm just curious, do you see the fact that you do have the ability to trade exercisable rights, do these exercisable rights give us a way to then interface with the non-digital world? Because can I exercise stuff that then has effects in the
yeah.
world?
So objects, oh, I'm sorry. The fact that these rights are exercisable, does that give us an ability to, I'm going to rephrase, but tell me if I got it right. Does that give us an ability to represent within the system rights to manipulate things outside the system in the physical world? And the answer is yes. And this very much builds on the fact that the answer with objects is already yes. We use our computer systems all the time to manipulate things in the world. Let's just take the example of a printer in a given office. So we might take the printer driver and abstract it up into a set of APIs that other objects can invoke for commanding the printer. But now you can wrap that right in an ERTP interface, and now you can manage the allocation of that right. Let's say this is a great example of use of it within an organization rather than a public blockchain, is you can easily just transfer the right from one place to the other, such that at any moment it might be an exclusive right to use the printer. Whether or not this makes sense for printer, several of the founders of Agoric had earlier founded a, well, I don't need to go into that. The answer is yes, that it's very straightforward to create that anytime you have software able to cause action in the world, you can abstract a wrapper around that, which is an exercisable right to provoke that software to affect the world. Yeah.
Oh, I wasn't raising a hand, but perhaps I'm the most curious about the use case. As for today, this year, who would be like top 3 companies who would benefit from adopting such technology?
I'm a technical person. I'm going to let Dean answer that one. Sorry, I'll repeat the question first. Who would be the top 3 companies, let's say, that would benefit by adopting these technologies?
So I'm also not going to answer that, but I'm not going to answer that because it's something where, A, it might not be a company adopting it that makes the biggest difference, right? And B, all of them will get different incomparable benefits from adopting this. As we saw in Professor Jason Pott's talk, the ability to reduce the cost of trust across trading resources, across trading stocks, across communication, across supply chain, across transport. The World Trade Organization noted that if they could deploy blockchain for tracking chain of custody of packages, that would increase the global GDP by 5% and trade by world trade by 15%. So it's one of those things where the value in all these different areas is just too hard to compare.
Yeah, so I'm going to pull from what you said something that is sort of an answer to that question, which is the real benefit of adopting this technology has to do with what happens between companies, much more so than what happens within companies, but both benefit.